Aloha and welcome to Business 621 Lecture 1 screencast on the basics of statistical inference. What we're going to do today is we're going to build on our uh, knowledge of descriptive statistics and apply it to making inferences or estimates about population characteristics from samples. So a little bit more on that later. But you can look through here and see the basic topics we're going to talk about. Now there are much more uh, extensive kinds of things in inferential statistics than this. This is just the basics, but this should give you enough foundation to actually move forward with other kinds of techniques and methods. Most of the other things are just variations on these basic things. One thing I want to point out, though, is you'll notice that we talk about things like inference for a single numerical variable, inference for a single categorical variable, inference for two categorical variables. You'll see kind of a running theme that just like in descriptive statistics, that after we understand what variables we want to look at what kind of data we're working with, and that will determine what kind of statistics we do. So more so than the questions that we want, they tend to be the same depending on what the kind of data is, but how we work with it will be determined by what kind of data it is. So we always want to keep in mind that we should know what is the data that we're working with it. What are the variables? Is it numerical? Is it categorical? Is it numerical and categorical? Blah, blah, blah. So keep that in mind as we move forward. The statistical methods that we're going to look at are estimation and hypothesis testing. And they're called inferential statistics because they differentiate from descriptive statistics in that in inferential statistics we're going to use descriptive statistics to see what we can infer or what we can sort of guess or say about something. And this something, the way that the general theme is that we have a population of things that we're interested in, and then from a sample of that population, we will look at the descriptive statistics of that and use that to say what we can infer from those descriptive statistics about the population. And the two main methods of things that we're going to look at are estimation and hypothesis testing. They're both related. So let's start with estimation. Now, to understand what estimation is, we start by understanding once again what's the difference between a population and a sample. So a population is any group of things that we're interested in. Now the interesting thing about a population is that it's not just data. It's actually a group of things that we're interested in that may or may not be observable, so or even accessible. Some examples of that might be that, let's just say we want to look at the average, the income of the American, the average American citizen or something like that. And now if we're talking about the population of current American citizens, that in one sense, if we freeze it in time, then that is a population that we can observe. But if we don't freeze it in time, we see that the population of the United States, in terms of citizenship, changes. It's constantly increasing and decreasing, or perhaps increasing, but it's changing. New people are added all the time, new people are born, etc., etc. People immigrate. So if we don't fix it at a particular point in time, that population actually is not observable. Because we can only observe part of it at any given time. We cannot look at it. But nonetheless, it does actually make sense to talk about a characteristic of that population. One characteristic we might be interested in is, say, the mean. And the mean of that population, let's say we're looking at the mean income of U.S. citizens, even though it's changing over time. Interestingly enough, we can even talk about a population of all U.S. citizens, past, present, and even future. So if we add future ones, that's kind of an interesting one, and it shows how the power of statistics, that we actually can do statistics about a population that has data that hasn't even occurred yet. So not only is it not something we can get our hands hold on because it's changing, but it may not even exist yet, and yet we can still talk about it. And that's one of the powers of statistics. Now, when we talk about a characteristic of a population, we usually mean some characteristic of some either a numerical characteristic of that population. Usually we talk about the distribution or a characteristic of that distribution for that population. So when we talk about a characteristic of a population, we will use a Greek letter, say mu. By convention, mu would be the population mean, and and we only look at the population mean for data that would be numerical. And we assume that when we have a population that that characteristic is not known. If the population turns out to be something that is very easily accessed and observed, let's just say the income of Dilemma students in our class, then all we have to do to get that population characteristic is ask every student in the class, the 30 or so odd people, what's your income? Sum up those incomes, divide by the number of people, and we have it. So that would not be an unknown parameter. It would be easily gotten. But if we look at the income, the average or mean income for the U.S. citizens, that is not easily gotten. Not only is it not practical for us to ask hundreds of millions of people what their income is, it's changing all the time, and so is the population, so we can't even get it. So in that case, it's actually unknown. Now the interesting thing is that even though it's unknown, that doesn't mean we can't say things about it. And what we want to do is say, take a sample of that population that we can access, that we can observe. And from that sample, we will calculate a statistic. In this case, the sample mean. And when we talk about a sample statistic, we will use the not Greek letters. In this case, for the mean, the convention is to use something like x bar. So x bar is just a notation to refer to the sample mean, whereas mu is the population mean. So we can distinguish one from the other by whether we use Greek characters or not Greek characters. And say we calculate that sample mean. Now it's a statistic because it's something that we can actually compute, meaning we take the values from the sample, sum them up, and divide by the total number of them. And let's say it was 50. Now the question we're going to know is how good is this as an estimate for the unknown parameter mu? In other words, this is a sample mean. Presumably it has some relationship to the unknown one. Why do I say that? Well, imagine that if this sample gets larger and larger and larger. As this sample gets larger and larger, say it tends towards the entire population, then the computation of the sample mean will converge towards the actual mean. In other words, once I get the entire population, that sample, if it is the entire population, is no longer an estimate. It is the actual population characteristic mean. So in other words, that there is a relationship between the sample mean and the unknown population mean. How good it is really what we care about. In other words, how accurate it is. And it obviously has something to do with how big the sample is, but it also has to do with a number of other characteristics and issues that we'll talk about. So there's a couple of important points to point out here. So one, the sample is a subset of the population that we can observe. From that sample, we do a computation or a statistic that is somehow related to the thing that we're interested in. And the question about estimation is how good of an estimate or an approximation is that sample to the thing that's unknown. So we call that the estimation problem. Something to point out here is it says that it's a random sample. So the issue here is that when we're doing estimation, we pretty much always assume that the sample we take is random. Random meaning that we did not select any of these points for any particular reason. Let's take, for example, the income of U.S. citizens again? Well, let's just say that our sample happened to be something convenient. Let's just say we went over to Kahala and we said, well, let's ask everybody who lives in Kahala what their income is. And then we sum that up and divide by that number of people that we asked, and we let that be the sample estimate for the unknown mean. Well, that's not going to be terribly representative of the population of the United States. Why not? Well, people in Kahala tend to be rather wealthy, and so the values that we're likely to get from them are going to be biased upwards or skewed on the higher income stream. That would be very different if, say, we went to Detroit and asked people in Detroit what their income is. Maybe their income tends to be a little lower. So in other words, if we are not random about this, if we are selective, then we will end up biasing our results, and that this approximation will not be representative of what the actual mean is. It will be biased or skewed one way or the other. And that means it's not terribly helpful. So we assume that the sample we have is random. Now, exactly what it means to take a random sample is a rather painful subject, so we're not going to talk too much about that. We're just going to go with our intuition here, which means close your eyes and just grab stuff from here. Okay, we'll just assume that that's our definition of random. Now, once we have an estimate, this is a point estimate, we make a statement about how good that estimate is. And when we make an estimate of how good it is, we can't just give a simple value. Usually we can express how good it is by giving it a range. So the value that we're looking for is between 40 and 60. Well, that's one way of looking at it, but then of course we need to know sort of, well, okay, maybe it's between 40 and 60. That kind of pins it down a bit, but we want to know, well, how sure are we that it's between 40 and 60? So we might say something like it's 95% confident. And we have to talk about precisely what this means. In statistics, all these things have very careful, precise definitions so that we're not ambiguous and that we're also reliable. Okay, so estimating unknown parameter population parameters. In our class, we're only going to look at a few population parameters of interest. In practice, of course, you can look at anything about a population that you might be interested in, and there's usually a sample statistic that will do that. But we're going to look at things like the mean. And when we talk about the population mean, we'll use the Greek letter mu, and then we'll talk about the sample statistic, or the estimator for it, being x bar. Similarly, now that would be for numerical data. For categorical data, we might be interested in the population proportion, and then we would estimate that with the sample proportion, which we'll denote by p. We might also be interested in the standard deviation. The standard deviation of the population we'll say is sigma, and for the sample, little s. We also might be looking at differences of means, and we might look at the differences of the sample means. We also, in our class, are going to be interested in things like the median, and but typically in other practices, especially if you're doing research, you might be interested in other parameters like correlation coefficients, covariances, and other various things. You can look at estimates for anything, but these are very common. So in terms of estimation, we have point estimates and interval estimates, and let's look at what those are. A point estimate is a single value, and we take a bunch of observations or random samples, and we take that random sample and we compute our estimate from a statistic, and that is indeed an approximation for our population parameter of interest. The problem with that is that we don't know how close it is, what error there might be, or how confident we are that that is a good approximation for it, or a representative approximation for it. So say we say our sample mean is 3, we call it a point estimate because it's just a single value, it's just a single point. And while it certainly says that our population mean might be about 3, we don't know how close it is to really 3. How sure are we that it is near 3 or actually is 3? An interval estimate is one step towards dealing with that question by providing a range of values. Now, the range of values will be based on, again, a sample, presumably a random sample. And what that does is it tells us how close we are to the unknown parameter, or how accurate it is. So when that interval says it's between this value and this value, on a low end and a high end. And the idea is that the smaller that interval is, the more accurate our estimate is, because the smaller the range is, means we pin that value down between a high and a low. So we sort of capture it, right? So we might say our unknown population mean lies between 50 and 70. So even though we don't know what value it is between 50 and 70, we know that it's somewhere in that range. And the smaller that range is, the more accurate it is. Obviously, if I said the population mean lies between 60 and 61, that leaves far fewer choices than between 50 and 70. So the length or the size of the range of the interval determines how accurate we are. Now, what's this business about 95% confidence? The 95% confidence comes in to say that we need to know kind of, well, even though that's an estimate, and we know it's between 50 and 70, or we think it's between 50 and 70, we could be wrong. And so when we say 95% confidence, we mean that 5% of the time it's actually not going to be between 50 and 70%. So 95% confidence means that 5% of the time I'm actually not going to capture it in there. And it's very important that you understand what I mean by capture. So let's talk a little bit more about that and what confidence are. So confidence level, you're going to hear this term quite a bit. Confidence level is the probability that the unknown parameter falls within the interval. So again, we want to know if we give a range, say, oh, it's somewhere between 50 and 70. We think it's somewhere between 50 and 70. We want to know, well, how sure are we that it's between 50 and 70? And one way that we can express that is with a confidence level. So the confidence level we denote by 1 minus alpha percent. And it's kind of curious that we say 1 minus alpha percent, because alpha is what we call the level of significance. And so alpha is the probability that the parameter is not within the interval. So in the case that we were talking about before, we said with 95% confidence, the mean population parameter lies between 50 and 70. So what alpha is 5%. Means that 5% of the time, it's not going to be between 50 and 70. 95% of the time, it is. So that's 1 minus alpha, 1 minus 5%, 95, right? If I take 1 minus 95%, I get alpha, which is 5%. So they're kind of opposites of each other. Now, typically for confidence levels, we choose confidence levels 90, 95, and 99, or anything between 90 and 99%. The reason for that is that, well, there's a relationship between how confident we want to be and the size of the interval. So the size of the interval tells how accurate it is and how useful it would be. So let's just imagine for a moment that we want to be 100% confident. Why is that a bad idea? Well, to be 100% confident, let's think about what we need to do, what interval size we'd have to have. Let's just say that we're estimating, once again, the mean population income for U.S. citizens. Well, we know it's going to be at least no less than $0. I guess you're not going to have negative income, but we don't really know how big it can be. You know, in principle, it could be arbitrarily large. Now, I know that Bill Gates certainly has a lot of money and has a huge income. It's not infinite, but we don't really know how large it can go, and somebody could just make even more than that. So when a practical level, you know, it can't be infinite, but we can't really be sure how big it can be. And even though if there's only a few people that might have that, we still have to take them into account. So what we'd have to do to be 100% confident we'd have to choose an interval between 0 and infinity. So to be absolutely sure, 100% sure, that we always know what the mean population income for U.S. citizens would be, we'd have to have an arbitrarily large interval, anywhere between 0 and 100, 0 and infinity. Well, that is not terribly useful as an estimate, right? I mean, it doesn't really give us any information. It's terribly inaccurate. It just says, yeah, incomes are some value, right, greater than 0. So that's not very useful. So what we do is we allow ourselves to be wrong. So we allow ourselves to be wrong, say 1% of the time, 5% of the time, or 10% of the time. Being wrong more than 10% of the time is usually not considered high confidence, so we don't usually accept it. Now, you could use lower confidence levels, but they're usually by convention not acceptable, because you'd be wrong too often. So let's just say we allow ourselves to be wrong 1% of the time. Well, if we allow ourselves to be wrong 1% of the time, let's imagine U.S. Citizens' income again. Well, look, let's say for most purposes, I'm really pretty sure that nobody in the United States has an income of more than, say, $10 trillion. I mean, that's a ridiculous amount, right? I mean, I could almost be 100% sure nobody has $10 trillion, but I'm not absolutely sure. But maybe I'm certainly 99% sure that nobody has an income of more than $10 trillion. So instead of giving an interval between 0 and infinity with 100% confidence, maybe I can say with 99% confidence the mean income of U.S. citizens is between 0 and $10 trillion. Great. Okay, and I would only be wrong maybe 1% of the time. Well, maybe I'm willing to be wrong a little bit more. So say I'm willing to be wrong 5% of the time. In that case, I can narrow my interval even more. So I said, well, I'm pretty sure that not many people, not maybe more than 5% of the people, have an income more than, say, $1 billion, right? $1 billion. So maybe with 95% confidence, I would say that the mean income of U.S. citizens is between 0 and $1 billion. Now, I could be wrong, maybe, but I'm not going to be wrong more than 5% of the time. And then you can see that the lower the confidence, the smaller the confidence interval can be. So, but the problem is it increases my chance of being wrong or not capturing it. So I can be more accurate or I can be more confident, but I can't be both. So let's talk a little bit more about what intervals and confidence levels are. The way that we're going to make our estimates, let's just say that we're making an estimate of the population mean. We're going to make an estimate by looking at the sample mean. Now the sample mean, we can consider the distribution of all sample means. The distribution means that if we take a random sample and we calculate the sample mean x bar, right, and then we throw that sample back into the population and we take another random sample and calculate x bar, you notice that those values, because it was a random sample, those sample means will be different, or it's very, very likely they'll be different. If we look at the distribution of all the values of the sample mean, let's assume that it's going to be bell-shaped or normal. It turns out that in most cases it will be bell-shaped or normal, and that's another amazing thing about statistics. But let's just take it on faith for now that the sampling distribution of the sample mean is bell-shaped, meaning that if we take a random sample and calculate the sample mean, and then we look at the histogram of all those sample means, it will look bell-shaped like this. Well, what can we say about making an estimate for it? So in other words, if we have a sample estimate x bar, right, how can we generate a confidence interval or confidence interval using that? Well, we know that the sample means will be spread out between negative infinity, infinity over here, or whatever it is, according to this bell shape. Now, right in the middle, we're assuming that if we take an infinite number of these samples, right, that the average of all those will be the actual population mean. So if we could take an infinite number of random samples, right, and look at the average of all those, it would be the population characteristic that we're interested in, which is the population mean. And that's going to be right here in the middle. So the question we have is like, okay, how close, given an x bar, what size interval could we get so that we know that we capture this mu 1 minus alpha % of the time, or equivalently, we don't capture it alpha % of the time. So let's say that we want to figure that out. So the way we can figure that out is if it's bell-shaped like this, right, then we know that we want to capture this center point here. Yes? So if we choose a value between here and here, right, then the probability that I'm outside of it on the high side is alpha divided by 2, and on the low side alpha divided by 2, because it's symmetric. So the probability that a value, that a sample, a random x bar is in this interval, right, is going to be 1 minus alpha. Let's make this more concrete. Let's say alpha is 90%. I'm sorry, alpha is 10%. So 5% of the time I'm going to be higher than this value. 5% of the time I'm going to be lower than the low value. And 90% of the time I'm going to be between here and here. Why is it 90% of the time? Because the area under this curve, okay, is 90% of the area under the curve. This would be 5%, that would be 5%. So this puts a precise definition to what we mean by 90% confidence. So let's say 90% confidence. Alpha would be 10. 1 minus alpha would be 90. What that means is that if I take a random sample and I calculate its sample mean, x bar, then this interval here will capture the mean, the population characteristic, 90% of the time. It will fail to capture it 10% of the time. Okay, so you'll see that I calculate a mean, a sample mean, and I look at a distance away from it on the low side and distance away from it on the high side, and I see, does that interval capture the middle? In this case, it does. In this one, it does. Notice it's shifted over. It's shifted over because the sample mean now is here. Oops, is here instead of over here. Okay, the size of the interval stays the same because we wanted to capture it 90% of the time. Now let's say I capture another random sample, and its sample mean is over here, going above and going below, so that I capture still 90%. Does no longer captures the population mean. So in this case, it's not capturing it, so it escaped. And then this one, it did. So if I did this, let's say I'm looking at 90% confidence. If I did this 100 times, if I have 100 of these confidence intervals, then 10 of them will be red and not capture them, and 90 of them will capture it. So that is a precise meaning of what we mean by 90% confidence that the value is between here and here. Okay, it means that when we generate these confidence intervals, that 90 out of 100 times we're going to capture this. Okay, if that's a little confusing, don't worry about it. In practice, it's a lot easier to deal with. So the question is, what affects the size of this estimate interval? Okay, well, one of them, of course, we already talked about, is the sample size. That the more samples we have, the smaller the size of the interval, the more accurate the estimate is going to be. And again, the reason for that is that the larger the sample, the closer it gets to being the population itself. And so once we become the population, it's no longer an estimate. So that interval better be, very, very, very small. Another thing that affects the size of the interval is how variable the data is, or the dispersion of it. So in other words, the more the data varies, like in terms of standard deviation, for example, then the larger the interval is going to be, because the values are bouncing around a lot. If I take a random sample of it, then what's going to happen is that it's going to be spread out, more likely to be spread out. So the values are going to be spread out over a larger range, which means I'm going to have to use a larger interval to try to capture the value that I'm interested in. And of course, the level of confidence. Again, the higher confidence I want, the larger the width, but the higher, the lower the accuracy. So if I want higher confidence, I get a larger width to capture, because I want to capture more of the things, be sure I capture it. If I'm willing to reduce that confidence, then I can be more accurate, but I have lower confidence. So there's always a trade-off between sort of confidence and accuracy. Let's talk about our first method. Now, our first method is, let's assume that our data is numerical, and that for that data, for that population, we're going to be interested in making an estimate of the population mean, mu. We're also going to assume that for not only is the population mean unknown, we're also going to assume that the standard deviation of that population is unknown. The reason why we assume that is that if we knew what the population standard deviation is, we probably would know what the mean is, because there's a relationship between the population standard deviation and the population mean. So if we don't know one, we probably don't know the other. So that for practical reasons, we don't look at. But it is possible that if we do know what the standard deviation is, we still can make an estimate, and we'd use a different technique for that. Those arise in the case where you want to set what the standard deviation is. So say that you want to assume in theory that it is this, or you want to force it to be a certain thing. Then you can say what is the estimate. But that's pretty uncommon. So usually this is unknown and that's unknown. Now for the data estimate that we're going to, for the numerical data that we're going to make the population estimate for, we're going to assume that it is normally distributed. It turns out that if we have enough sample points, that this is not an issue. But if you only have a small number of sample points, this is. And the reason why I want to assume it's normally distributed is for this, because we want to be able to precisely calculate the probability that I'm in an interval or I'm not in an interval. So to calculate that probability, I have to know the distribution. So if I know the distribution is normal, then I can calculate what's the probability that I'm this or greater. What's the probability that I'm that or smaller. And because of that, I can calculate what's the probability that I'm in or not in this confidence interval. So to calculate those confidence intervals, to put precise meaning to 95% or 90% confidence, I have to assume that the population is normally distributed. So let's just take an example here. Let's just say that I'm analyzing the time it takes to do a particular task, and I observe a sample of times to complete a task of being 3.6 minutes, 4.2 minutes, 4.0 minutes, 3.5 minutes, 3.8 minutes, and 3.1 minutes. So this would be our sample. We would like to know what is an estimate for the mean task time in general for the population based on this sample of observed task times. And let's just say we want to be 90% confident. So we'll allow ourselves to be off or wrong 10% of the time. How accurate of an estimate can we make? Well, what we can do is we can use Megastat to do the calculations for us. Now, we could go through all the technicalities of how to do this, but I don't think it's particularly illuminating. I think you know enough of the theory behind this already without having to know how to do the calculations. Let's just let Megastat do the work. So what we would do is we'd open up Megastat, and calculate a confidence interval under the confidence tab. And we would calculate, let's take a look at what that is. Let's see if I can get that up. Okay, so let's say I have this data. And so what I want to do is go to add-ins, Megastat, and I'm looking for confidence intervals and sample size like this, and see it brings up this window similar to this. Notice that it asks for the confidence interval mean, confidence interval p if it's a depending on what I'm estimating here. It's asking for the confidence interval for the mean, confidence interval for the population proportion, sample mean, sample size, and that kind of stuff here. Okay, so if I compute, let's see, the sample mean here, so I just say average here and calculate that like that, I get 3.7. Okay, and I calculate the sample standard deviation. And now let's go to Megastat, confidence intervals, 3.7, standard deviation of 0.389872. Sample size is 1, 2, 3, 4, 5, 6. And I want my confidence level to be 95%. Now what I want to do is, you see it says Z or T. And the reason why what I would choose between the z-test or the t-test depends on the distribution I'm willing to assume. The z-test is if I know the standard deviation and I want to estimate the unknown mean. The t-test is if I have an unknown standard deviation and an unknown mean, which is our case too. So in that case I'll do a preview and you'll see I get an estimate of 3.291 and 4109. Okay, so let's hide that. And what that says, I say again, t-test, that was 95% confidence. I guess 90% confidence, you get the idea. Is that with 90% confidence, the population mean times will fall between 3.379 and 4.021. Okay, so that's all we're going to talk about with confidence intervals. To calculate confidence intervals of proportion, it's the same thing. You just choose the sample proportion instead of the sample mean. And for any other estimate for other parameters, as long as you have something calculated, that's how you do it.